Okay, so I will be speaking about understanding isolated and satellite galaxies through the use of the ART code, which is the Adaptive Refinement Tree Code. It's a hydrodynamical code written by Anatoly Klipin and at the time his former grad student Andrei Kravtsov in the late 1990s. And I would first off love to thank the Blue Waters and NSF for their funding as a Blue Waters graduate fellow. This has enabled me to bring this project together and also get the computing time in order to run it. So without them, this project would not have been possible. So in general, my goal is to get a better understanding of galaxy evolution. And there are many components of understanding galaxies. And here you can see this beautiful image of M31 by Robert Gendler. And you can see that there are a lot of different components in galaxies that we need to understand. We need to trace the gas, the stars, and also the dark matter in order to understand what's going on with galaxies through cosmic time. And we also, I would love to learn more about dwarf galaxies, where dwarf galaxies are just small galaxies, both satellite galaxies, galaxies that orbit another host, or isolated galaxies, those dwarf galaxies that are further away. So you can see here M32, right here in this corner. So this is an example of a satellite galaxy. So I want to learn more about how dwarf galaxies evolve and a little bit more understanding of what it takes to create different kinds of dwarf galaxies. So an understanding of galaxy evolution requires a lot of things that can pose a challenge. There's a wide dynamic range in terms of you need a large volume, but also high spatial resolution. We want to run the code for a long time span for the age of the universe, but we also need good time resolution in order to capture the physics of star formation and feedback. And we also need to follow dark matter particles, create stars, also introduce feedback from star particles, and follow the gas flows. And a bigger challenge is in understanding dwarf galaxy evolution, we need even higher resolution. And we want to have better resolved volumes in order to track what isolated dwarf galaxies are doing that are towards the edges of the virial radius of a main host galaxy. So we want to track both, we want to have a larger volume that's better resolved and even higher spatial resolution. And that's where we need the supercomputing time. So here we have an image from Oliver Hahn and Tom Abel of the cosmic web. So this is a larger zoom out for those of you who have never seen what the universe looks like on large scales. This is the dark matter structure, and you can see there are all these filamentary structures and the small dots. So one of these dots, like over here, would be a Milky Way mass galaxy, so something pretty massive. So on the largest scales, you can see that we need to have a big enough volume that we're able to have a representative section of the universe. You don't want to be selecting a region that's too underdense or too overdense if you're trying to look at isolated dwarf galaxies or Milky Way type galaxies. So that's on one end of the dynamic range. And on the other end, if you look at galaxies edge-on, you want to be able to resolve this thin disk in order to make realistic looking galaxies, especially spiral galaxies and dwarf galaxies. So there we have about an order of 1 million in spatial range. And also you can see that these small clumps where stars form in spiral galaxy arms, you also need high spatial resolution in order to resolve that star formation and feedback regions. So why does this matter? Well, there are still discrepancies between theory predictions. So what ΛCDM dark matter only simulations are able to produce in terms of simulations and observations on the smallest scale, and those small scales are galaxy scales. So we want to be able to check that observations that say that there are fewer dwarf galaxies than dark matter only simulations predict, and that they're less dense. We want to check that with simulations that should reproduce the universe, including gas, in addition to dark matter and stars. So we want to gain a better understanding of all these different questions, a few of which depend on specifically satellites of larger galaxies. So here's a visualization where you can imagine that you just put a galaxy, like our own Milky Way, in the center here, and then you can see its dark matter halo surrounding it, and then all these blue objects are different dwarf galaxies that are satellites of the Milky Way. And this is what dark matter only simulations predict, that there should be thousands of dwarf galaxies surrounding an object like the Milky Way, some of them more massive and some pretty small. But when we look at observations, we find that there are only an order of a dozen massive dwarf galaxies and more less massive or ultra-faint dwarf galaxies around the Milky Way. And if you look at the entire local group, you get a couple more. You get twice as many when you add up Milky Way and Andromeda, and you have some more isolated dwarf galaxies, but it's not on the order of thousands like we see in simulations. So we'd like to understand that a little more and understand why dark matter only simulations predict there to be more dense and more massive galaxies, dwarf galaxies. So in order to do that, what we've done is we're going to try to create galaxies that are realistic. They need to be able to match observations, but we also need them to be high resolution in order to examine the smallest scales, so the central density cusps or cores of dwarf galaxies, and also capture those smaller ultra-faint dwarf galaxies. And we're going to use these simulations to learn about dwarf galaxies in general, in terms of their abundances, star formation rates, their morphological changes that they may undergo when going from an isolated dwarf galaxy to a satellite dwarf galaxy. So the tools we've used to create simulations and learn about dwarf galaxies is the ARC code, as I previously mentioned, which is the adaptive mesh refinement code. It includes hydrodynamics, dark matter particles, and star particles. And our star particles, we have a treatment for feedback and star formation. We have options for probabilistic or deterministic star formation modes, as well as stellar feedback in the form of stellar winds, supernova feedback, type 1 and 2, and also radiation pressure and photoionization pressure as well. And we also include metal advection in our simulations. So we have realistic physics that we want to include in order to simulate our galaxies. And in order to do that, we use zoom-in initial conditions. So in order to get around the issue of having a wide range of spatial scales that we need to examine, we use zoom-in initial conditions. So we simulate a large simulation volume, and then we zoom into an object of interest. And from there, that's where we place, that's the object that we're going to track. So in order to do that, we place our highest resolution dark matter particles in that central region. And then we are able to achieve both the large simulation volume and the high spatial resolution that we need to track dwarf galaxies. And that also allows us to run for the age of the universe while also having good time resolution on those lowest levels. So in our tree code, we have multiple levels of refinement, and our lowest, and in the central region of the galaxy, that's where most of the good time resolution, that's where our lowest levels are. So what have I accomplished over this past year? Well, we've worked on code development because we've needed to modernize our code a little bit. There were some things that hadn't been looked at in a while. And we were able to produce a significant increase in code speed depending on the initial conditions, factor of 10 to 50. And in addition, we've generated 25 new initial conditions of massive galaxies with well-resolved surrounding regions that we are going to start to run with the new version of the code we've developed. And we've run some parameter tests on isolated dwarf galaxies in order to ensure that we match observations that need to be matched, like the Kennecat-Schmidt law. Another piece of data software that I created was I've worked on creating a pipeline, a workflow for data analysis routines that are able to be run on all of our simulations, combining Fortran code, Python code, and YT. And in addition, I've completed some analysis of simulations run by another member of our group, Danielle Severino, who has run a suite of simulations called the Vela simulations. And these simulations, I used our new analysis workflow, and I was able to get results from those objects. And that's what my poster's about. So if you'd like to hear a little bit more about the science of that, you can come talk to me afterwards. So in terms of software products, some of the things we're able to do to speed up our code were we hadn't realized that most of our time in our density calculation had been going to some serial loops that we thought were going to improve the speed of the code, but It didn't, so we were able to fully parallelize our density calculations, implement better I/O practices. We also implemented a new algorithm for star particle resampling in order to reduce the number of old stars that aren't doing anything in our simulation any longer. And that is a huge increase in terms of the speed of our code, so that can be a factor of 10 or more depending on the number of stars that we actually create. And we've also examined testing different refinement schemes, and that we're just beginning this work, and so far we don't have any results for that, but it looks like that could be another factor of 2 or more. And I introduced a new feedback implementation for radiation pressure that ensures that even at very high resolution or very small time scale, we're not overproducing the amount of pressure in terms of overpressurizing these zones where there is star formation. And in terms of analysis workflow, I created a pipeline to have our data analyzed by Rockstar halo finding algorithm in order to find the centers of all our dwarf galaxies, which can be difficult to track through time. We also introduced new profiling tools with our Fortran code and particle finding algorithms, as well as Python plotting and analysis routines. And I've been working with the YT code and the YT community in order to create compatibility for the ART code. So here's a quick intro about those simulation results I was talking about. So these are the velas. These are the codes. This is the simulations that's been run by Daniel Severino. So we have a couple different versions of these initial conditions. There's 35 initial conditions, and they've been run with different forms of feedback: supernova only, supernova plus radiation pressure, and then that plus photoionization heating as well. They all have box lengths, the same box lengths, resolutions, and dark matter masses. And here's just a projection of the entire simulation box. And these results are the ones including radiation pressure. So here's just some eye candy of over a 2 megaparsec region centered on the main halo. You can see there's high density regions in dark and low density in light, low temperature in these dark regions, and then high temperature in these white regions. So we're blowing out regions of high temperature here, and then this is metallicity, where these are higher metallicities, and this is absent of metals in black. And so here on my poster, I'm showing results from 10 of the Vela host galaxies. These were not selected for specific environments, so they weren't selected to be particularly isolated, just isolated enough to run them down to redshift 1. These simulations have only been run to redshift 1, and so with the new version of the code that's increased in speed, and our new initial conditions that have a much larger region around them that is well resolved, we're going to be able to run those down to redshift 0, so that's the reason we want those new initial conditions. But these velos have a range of halo mass of 10 to the 11 to 10 to the 12. And the only result that I'll show here is just the distributions of satellite galaxies around one of the main halos. So you can see here's the center of that galaxy, here's the virial radius, or the edge-ish, kind of. There are no edges to galaxies, but the edge of this main galaxy. And in blue are all the luminous dwarf galaxies, and in black are all the dwarf galaxies that did not form any stars. So you can see that there doesn't seem to be a specific distance relationship between the two. It's not like all the dark galaxies are within the virial radius. And I have a lot more results about these galaxies on my poster. And so we have a lot of stuff to work on in the future. I need to run those 25 new initial conditions with the improved version of our code. It has a large volume, 100 megaparsecs, roughly twice the dark matter particle mass and physical resolution of the previous run. And this will allow us to run it down to redshift 0, so that's why we had to kind of degrade our resolution a little bit. We're going to produce about 500 outputs per simulations, and so I need to update the workflow to parallelize it and speed it up, because right now it's not fast enough for 25 different initial conditions, each with 500 snapshots, and include some time series analysis to do some merger trees, figure out how those dwarfs move through time, be able to track them and find their peak masses and circular velocities. And then I need to run that workflow on these simulations that I'll be running over the summer on Blue Waters. Select those isolated and satellite dwarf galaxies and look at all the interesting science results we want to find out. about their stellar masses, star formation rates, the number of satellites, how they merged with their main galaxies, how much tidal interactions influence them, how much do they contribute to the luminosity function at high redshift, are they contributing significantly to the circumgalactic medium in terms of the metallicities of the host galaxies? There's a lot of interesting questions we can look at, and of course looking for cores or cusps. We'll try to see if that's possible with our resolution. We think it likely is. So finally, I would really like to thank the Blue Waters Graduate Fellowship, as well as all the people who have helped me from Blue Waters in terms of helping me with code and other stuff, as well as my advisor, Anatoly Klippin, who's really helped me improve the speed of the code in terms of generating the initial conditions, and it wouldn't have been possible without his help being on board on this project, and as well as postdocs Daniel Severino and Sebastian Trujillo Gomez, who have contributed different parts of the code. And finally, Matt Turk, who has been wonderful in terms of giving his time to helping the art code be able to be read in by YT, and been really welcoming in terms of accepting new members into the YT community. So thank you.